For centuries, science operated on a comfortable assumption. Reality exists entirely independent of us. The moon is there whether you look at it or not. A falling tree makes a sound, even if nobody is around to hear it. By the late 19th century, physicists believed they had this reality almost completely mapped out. Newton's laws described motion, while Maxwell unified electricity and magnetism. The universe looked mechanical, a predictable cosmic clock governed by deterministic laws. But when scientists looked closely at light, the clockwork refused to turn. When they heated metal in the lab, the light it emitted contradicted existing physics entirely. This chart illustrates the problem they called the ultraviolet catastrophe. Classical equations predicted that as an object got hotter, its ultraviolet radiation should spike into infinity. The mathematics produced nonsense that the observed data clearly rejected. In a desperate attempt to fix the equations, physicist Max Planck proposed something absurd. He proposed that energy arrived in tiny, discrete packets called quanta. His equation, E equals hf, showed that energy was tied to frequency in fixed chunks rather than flowing as a smooth, continuous wave. To save physics from mathematical failure, scientists took the first step in dismantling the concept of a continuous, objective reality. In 1905, Albert Einstein studied the photoelectric effect, building upon Planck's mathematical solution. Classical wave theory predicted that brighter light should eject more energetic electrons from a metal surface, but experiments showed that intense red light did nothing, while very dim ultraviolet light ejected electrons violently. Einstein realized light was behaving as localized bullets. These photons carried fixed energy, meaning their power came from their frequency rather than the intensity of the beam. Light was now caught in a physical contradiction. It acted like a wave in some experiments and like isolated bullets in others. Reality was beginning to fracture. This contradiction escalated with the double-slit experiment. Scientists fired light toward a barrier containing two narrow openings, with a detection screen sitting behind it. If light were made of distinct particles, you would expect to see two distinct impact bands on the screen. Instead, an interference pattern emerged, alternating bright and dark regions. The light passed through both slits simultaneously, overlapping and interfering with itself as waves. To test if solid matter behaved similarly, physicists replaced light with single, isolated electrons. They fired these particles toward the barrier one at a time. Even though they were fired individually, the single electrons eventually formed a wave interference pattern on the screen. Each particle behaved as though it traveled through both slits at once. Matter itself possessed probability waves. Solid, definite objects were actually distributions of possibilities, traveling multiple paths simultaneously. Physicist Erwin Schrödinger mapped this behavior mathematically, creating a wave equation that governed all these possible states. Under this model, a particle does not have a definite location before measurement. It exists as a smeared cloud of statistical possibilities. When scientists placed detectors at the slits to observe which path the electron took, the interference pattern vanished. Unmeasured particles behave as waves of possibility, while measured particles behave as ordinary, localized objects. Physicists eventually ruled out physical disturbance from the instruments. In refined experiments, the mere availability of information about a particle's path, even when the particle is not physically touched, causes the wave function to collapse into a single state. Niels Bohr argued that quantum objects possess no definite properties until they are measured. Werner Heisenberg formalized this into the uncertainty principle. He proved a trade-off. Knowing a particle's exact position makes it impossible to know its momentum. This animation illustrates a limit of the universe. Because of the math governing these waves, position and momentum cannot exist in a perfectly defined state at the same time. Uncertainty is a mathematical constant of the universe. No technological advancement can overcome this built-in limit. Einstein resisted this probabilistic view of the universe, arguing that God does not play dice. But the experiments favored quantum mechanics, especially with the discovery of entanglement. Two interacting particles could become linked so completely that they operated as a single system. Measuring one particle instantly determines the state of the other, even across enormous distances. No signal traveling at light speed could explain it. Einstein called it spooky action at a distance. Entanglement implied that reality is not locally real. The universe operates through invisible connections that classical physics deems impossible. In 1964, physicist John Bell converted these philosophical arguments into mathematical inequalities that could be physically tested. Repeated experiments consistently violated Bell's inequalities, proving that particles hold no definite state before they are measured. Today, this observation-dependent mechanics powers lasers, MRI scanners, and the quantum computer processors seen here. The equations predict nature with precision, even if the meaning remains debated. The violation of Bell's inequalities reveals that properties emerge only through the act of measurement. This suggests the universe reaches a definite state only when we engage with it. We are active participants in the creation of reality.